Alright, so picking up where we left off with the Olympic archer problem. So this archer is able to hit the bullseye 80% of the time. So it sounds like the probability of success, little p, is going to be 0.8. And the probability of failure is going to be the other 20% that we don't hit. We assume each shot is independent of the others. So that means we should be able to use a Bernoulli trial situation. So binomial geometric models will work. Assume each shot's independent. If she shoots 6 arrows, okay, so n equals 6. So when we have binomial situations, we're going to have an n of 6. What's the probability of each of the following? Now, just because we predetermine a number of shots doesn't mean that every question is going to be binomial in nature. It really just depends on how the random variable is defined. So let's start with part A here. What's the probability that her first bullseye is on the third arrow? Oh, the first one, that's geometric. This is a geometric distribution because we're going to shoot until we get a winner. So we're going to get a winner on the third. So even though we know that she's going to shoot 6 times, we only worry about what happens on the first 3 and that she wins on the third. So probability of a success on the third trial, x equals 3, means that she misses the first 2. So 0.2 times 0.2, which is 0.2 squared for her first 2 misses. And then she hits the third one, 0.8. So if we grab our calculators and crunch that out, that's going to come out to 0.032. So about 3% of the time, she's going to get to the third arrow before she hits her bullseye. She's an Olympic shooter. It should be rare for that to happen. So that makes some sense. Okay, part B. She misses the bullseye at least once. Okay. At least one is the situation we've seen before. That one's easiest if we do it in terms of the complement. So 1 minus the probability of she never misses. So no misses. Okay, so no misses means she hits all 6. So probability of all 6 are bullseyes. We don't even really need a binomial or a geometric here. We can just compute that. If all 6 are bullseyes and she has an 80% chance of hitting a bullseye, then she has 80% times 80% times 80% times 80% times 80% times 80%, which is just 80% to the 6th power. And if we subtract that from 1, we'll get 0.7379. So this is back to just the old use a complement. So kick back to chapter 13 and 14. Those do actually come back occasionally, and we have to still remember how to do them. Alright, part C. Her first bullseye comes on the 4th or 5th. So the first bullseye implies that this is geometric, and we could hit it on either the 4th or the 5th. So we want the probability of x equals 4 or x equals 5. Okay, so that means we'd miss the first 4. Sorry, on x equals 4, we'd miss the first 3. So we'd have 3 misses, 0.2 to the third, times 1 hit, that's 0.8. Or means to add. To get x equals 5, we'd miss the first 4, so 0.2 to the 4th, times a hit, which is 0.8. And we can crunch that out with a calculator, or we could use a handy dandy tool that I didn't show you yesterday. Turns out, if you go to menu, probability, distributions, and you scroll way on down there, there are geometric PDFs and CDFs that you can choose from. PDF is for one x value, CDF is for multiples. So let's do the CDF. That's J. Nope, I. Press I. Probability of success is 0.3. The lower bound is 4 arrows, 4 bullseyes. The upper bound is 5 bullseyes. And if we crunch that, we get about 0.1743-ish. I have the wrong probability. We're going to have to redo that one because Ms. Rice pushed the wrong buttons. Let's try again. Probability, distributions. Actually, I can scroll upward since it's toward the bottom. Do geometric CDF. Let's try again. The probability of success is 0.8. I'm shooting arrows down. I'm not pulling speckled M&Ms out anymore. I've lost my train of thought there. So 4 is the lower bound, 5 is the upper bound. And that's more like it. So 0.00768. So 0.00768. All right. Part D, she gets exactly 4 bullseyes. Now, to get 4, you have to shoot all 6 of them. So we're back in binomial world here, because it's not about when the first one happens, it's about how many total she has. So if I'm going to hit exactly 4, that's a binomial where the probability of the number of successes equaling 4 is what we want to compute. I have a formula for that. It says take the combination of 6 arrows, 4 of which we want to hit, so we want 4 successes, and then the probability of success, 0.8, that happens 4 times, 0.8 times 0.8 times 0.8 times 0.8 for 4 successes, and then failure, 0.2, is going to happen the other 2 times. Now we can either crunch that out on the calculator, or we can use our probability menu, distributions, binomial PDF, that's A down there at the bottom. So if I have 6 trials, that's 6 arrows, with an 80% chance of success, 0.8, and my X value is just 4, then the probability that that will happen is 0.2458-ish. So you can use that tool, or you can use your combination tool and just key it in the way that it is on paper. Alright, we're on the home stretch. We just got one more page to look at. So 2 more bullseyes questions. Alright, so we want at least 4 bullseyes. So that means we could get 4, 5, or 6. So we can either write that as the probability of X is at least 4, greater than or equal to 4, or we could say the probability of X is equal to 4, or X is equal to 5, or X is equal to 6. The first is more efficient, but this one maybe has a little more meaning to it. So if we get it on the, if we get 4 of them, that's 6 arrows with 4 successes, combination of that, 0.8 to the 4th times 0.2 to the 2nd, 4 successes, 2 failures, or plus 6 arrows, 5 are successes, so 0.8 to the 5th and 0.2 just to the 1st power, plus 6 arrows, all 6 are successes. There's only one of those. 6 over 6 is always going to equal 1. And then 0.8, 6 of those, 0.2 to the 0. So I'm just going to leave it off. That means it's just a 1, so it doesn't matter. And then I can either crunch that all out on the calculator, or I can use my tool one more time. Menu, probability, distributions. I'm going to scroll from the bottom. It's about the same distance from the bottom or the top. Binomial CDF, since I have more than one X value. I have 6 trials. 0.8 probability of success. My lower bound is at least 4. Up to 6 is my upper bound. And that's equal to 0.9011-ish. Hope I put the right numbers in that time. Yep. So 0.9011-ish. Last one. She gets at most 4 bullseyes. This is not the complement of this, by the way, because they both include the 4. So don't just subtract this one from 1 and think you have it. At most 4 includes the 4, but so does this one. So that means probability that X is less than or equal to 4, which means she could get none, or 1, or 2, or 3, or 4. So probability of X equals 0, or X equals 1, or ... all the way up to X equals 4. So let's get this one set up. So we can shoot 6 arrows, get none in, which means no successes, but failures we got 6 of. So 0.2 to the 6. All we have to do is count failures there. Plus, we could shoot 6 arrows, one of them be a bullseye. So success, 0.8 to the first, and then the other 5, 0.2 to the 5th are failures. Plus, now I don't want to do 3 more of them, so I'm going to do ellipses and then show where it ends. So the last one is 6 arrows, 4 of them are successes. 0.8 to the 4th for 4 successes. 0.2 to the other 2 power for the 2 failures. Definitely don't want to key all this in by hand. So we'll go back to our shortcut menu, probability, distributions. B is binomial CDF. I know it's the next one down the list, so I'm not going to scroll. I have 6 successes. Sorry, 6 trials. 0.8 is the probability of success. Lower bound, notice the lower bound is by default 0, so I won't need to change that. And then my upper bound is 4 successes, and the probability of getting that is 0.3446-ish. So 0.3446-ish. Alright, so the very last slide in this little chunk is this little slide on the calculator instructions. So this will nail down when to use your geometric PDF, geometric CDF, and the binomial PDF and binomial CDF with examples. So PDF is always for just an equal to one X value. CDF always works for a range of values. So when you have a list of more than one probability added to others. Alright, and that'll wrap up this lesson. Your next homework is on the next slide of the PowerPoint from page 431. If you don't have your book with you, you will find scans in Schoology, and you can use those scans to do that work. You can do that work on your own paper, and either you can scan in a picture and send it to me, but if you want to just hang on to it until we get back from our snow days, you can hand that hard copy in as usual, and then I'll just put a grade in Schoology for that. Alright, if you have any questions, you can email me, and I will get back to you as quickly as I can. Enjoy your day.